Hi, Assalamualaikum and a very good morning. So today we're going to do some tutorial discussion for chapter 5, focusing on the subtopic of 5.2 alkene. We're going to do tutorial question 2, 3, 4, and 5. Also, we're going to do tutorial question 8 and 9. And last but not least, we're going to do tutorial question 10, 11, and 12. For the reaction mechanism, we're going to look at that in our physical class. Without any further ado, let us start. So for tutorial question 2, we have to draw the structural formula for each of the following alkene. So given here is the naming of the alkene, which is 1,2-dichlorocyclobutene. So we have to identify the parent name first, which is the cyclobutene. So cyclobutene will have 4 carbon, which is in cyclic form, 1, 2, 3, 4, and one of the carbon-carbon bond gonna be the carbon-carbon double bond because it refers to butene. And then the cyclobutene gonna be attaching with chlorine atom, which is 2 chlorine atom, and that is why the name is di. So we're gonna put the chlorine at the carbon-carbon double bond here as Cl and also Cl here because the carbon-carbon double bond will be named as number 1 and number 2. Okay, you cannot do Cl and Cl here because the double bond going to take number 1, number 2, and number 3. So for this case, this is not what is required. What's needed is here. Okay. And now for structure E, which is trans 1,2-chlorobutene. So the parent name here is butene. So you know that it needs to have 4 carbon chain, which is 1, 2, 3, and then 4. Okay, so this is butene, and then it's gonna be 2 butene. So it's gonna be here. Okay, 2 and 3, but then we take the earlier one, which is butene. And then at carbon number 1, it will be attaching with chloro. Okay, so carbon number 1 attaching with chloro. Okay, and if I were to expand the structure a little bit, so I can say that what hidden here is hydrogen, and what hidden here is hydrogen. Okay, so at carbon-carbon double bond here, I will have this chain and will have CH3 here, which is carbon number 4. Okay, so this is my trans isomer because my hydrogen is at the opposite side. Okay, so alternatively, you can also draw it this way where they flip the structure. So CH3 gonna be on the left hand side and H gonna be on the left hand side. And H gonna be on the right hand side, CH2Cl gonna be on the right hand side. So you can draw it this way or you can also draw it this way, doesn't matter because it still be the same structure. Now moving on to the tutorial question 3. The following names are incorrect, suggest the correct name. So first that we need to do is we need to draw the structure first. So we have trans 3-pentene. Okay, so you know that pentene will have 5 carbon, right? Okay, so 5 carbon and 1 double bond because it in. So 1, 2, 3, 4, and 5 carbon. And then it will have a carbon-carbon double bond at number 3. Okay, so they thought that number 3 gonna be here. Okay, and if I were to expand the structure, gonna be hydrogen here and gonna be hydrogen here. So this shows that it is a the trans structure of the 3-pentene. Okay, so they thought that the name is going to be trans 3-pentene, which you thought it is right, but actually this is the wrong name. It's supposed to be, okay, so I can do the numbering. Actually 1, 2, 3, 4, 5 is incorrect because I should do the numbering from here. 1, 2, 3, 4, and number 5 here. So I will the name gonna be trans to pentene. Okay, because I need to take the lowest number as the name. Okay, so the double carbon double bond gonna be attaching at 2 and 3 instead of 3 and 4. So I will take the number 2 here. Okay, at carbon number 2 and carbon number 3, but then I will take the smallest number as the naming, not 3 and 4. Okay, so 3 and 4, the one in red is wrong. Okay, so also you can also draw it in terms of, okay, you can also draw it in terms of the expanded structure if you like, or you can also draw it in the way that I drawn just now. So both are basically correct. And the name supposed to be trans to pentene because it will be at carbon number 2 and carbon number 3. So it should be number 2 instead of trans 3 pentene is wrong. Now we're going to do B, which is 2-methyl cyclohexene. So the parent chain going to be cyclohexene, where it has 6 carbon. Okay, and then one of them going to be double bond. So the double bond going to be labeled as 1 and 2, and then the methyl is attached at carbon number 2, which is CH3 here. Okay, so the structure here is correct, but what is wrong is the numbering. So we should do, instead of do 1, 2, 3, 4, 5, 6, we supposed to make the numbering as number 1 here, number 2 here, and then everything change into sequence 3, 4, 5, and 6. So it's supposed to be 1-methyl cyclohexene. Okay, so you can draw it this way, or you can also draw it this way and name it as 1-methyl cyclohexene. Now for tutorial question 4, we have to write an equation to prepare for the preparation of propene from the 2-chloropropane. So you know that your starting material going to be 2-chloropropane, and then anda kena menyediakan propane. So the idea is your product gonna be propane. So propane gonna have 3 carbon. So 1, 2, and 3. So propane, and then one of them gonna be having a double bond. So this is your target. Kena menyediakan benda ini daripada 2-chloropropane. So your starting material is starting with chloropropane. So propane gonna have 3 carbon, which is 1, 2, 3, and then chlorine gonna be attaching at carbon number 2. So from here, you need to prepare this one. So you know that you need to undergo the process of dehydrohalogenation. So you need to remove hydrogen, hydro, and then you need to remove halogen, where halogen refers to chlorine. So you can remove chlorine from here and hydrogen from this side. Or you can also remove it from this side because it is still the same. So you can use the skeleton structure as I use, or you can also write it in terms of the condensed structure or expanded structure, whichever you feel you feel better with. Okay. Okay, so this might be the expanded structure, and then you're gonna react that with the KOH and also an ethanol. Okay, so this is compulsory to write because this is the reagent needed, and then the product that we're gonna get is this product, and this reaction needs to happen at high temperature. So this is compulsory. The same goes to this compulsory because this is going to provide a basic medium for the reaction to take place. So the chlorine and the hydrogen gonna be removed out, and the single bond gonna be eliminated, and carbon double bond gonna be formed. So you can also write it as here or do it as mentioned here. Okay, now for B, we're gonna prepare propane, which is the same product. Okay, but now from a propanol. So propanol gonna have 1, 2, and 3 carbon, and then we have OH as the functional group. Okay, so it doesn't say 2 propanol, so you know that OH gonna be at the end. Okay, so you can put the OH here or the OH here, but you just need to change the numbering 1, 2, and 3. Okay, so now in order to prepare propene from propanol, you know that you need to um, remove hydrogen and alcohol, the hydroxy group here. So you need to remove water. So because when water is being eliminated, a carbon-carbon single bond is formed. So here will be the same as here because you can choose the left hand side or the right hand side. Okay, so let's say if I draw the molecule of the propanol to be in the condensed structure here, and then reacted with the reactant, which is the concentrated H2SO4, which is acting as an acidic catalyst. So the reactant here need to be written separately, and then this gonna produce, they will mix together, and this reaction happens at the high temperature. So this is compulsory, and then this gonna produce a propene. Okay, so if I were to expand the structure here, H OH, and then we have CH H, and then the balance is CH3 here. HOH here is being removed, and as a result, a carbon-carbon double bond is formed. So that is why it's written as CH2 double bond, CH and CH3. Okay, so that's for tutorial question 4. Now for tutorial question 5, we have to outline the preparation for the 1,2-dipromocyclopentane from bromocyclopentane. Okay, so sekarang kita kena menyediakan 1,2-dipromocyclopentane daripada bromocyclopentane. So in order to make your life easier, it is highly advisable to start drawing the reactant, which is bromocyclopentane. So cyclopentane will have 5 carbon, 3, 4, 5, 1, 2, 3, 4, 5, and then the bromine going to be attaching here. Okay, so you can choose whichever carbon that you want because it only has one substituent. So from bromocyclopentane, you need to attach 2 bromine atom here. So what you're going to do is you're going to dehydrate the you need to remove HBr first so that you can form a carbon-carbon double bond, and then you're gonna add up with bromine so that you can add up more bromine molecule instead of one. Okay, so let me show you step by step. Okay, so this is our starting material, and then if we were to undergo the process of dehydrobromination, yang mana kita akan remove hydrogen and also Br, what we're going to have is cyclopentene. Okay, so I can remove the hydrogen from here and the bromine from here, or I can remove hydrogen here and Br here. Okay, so if I were to remove, I will get a carbon-carbon double bond here. Now I'm going to produce 1,2-dipromocyclopentane. So I'm going to react the cyclopentene that I have with the bromine molecule in the inert solvent. Okay, so this process is known as the halogenation. Okay, and this is the inert solvent. In your lecture note, I'm using CH2Cl2, which is dimethyl dichloromethane, or I can also use tetrachloromethane, doesn't matter because both are inert solvent. So when I add up bromine molecule into the system, Br and Br here gonna be added. Okay, and that is where we forming 1,2-dipromocyclopentane because it's gonna be number 1, number 2 here, and this structure here is known as cyclopentane, and then bromine is attached at carbon number 1 and carbon number 2, and then because it has 2 bromine atoms, so it's going to be dibromocyclopentane. And this is how you outline the preparation. Do it step by step. Okay, now for question B, we have to prepare chlorocyclohexane from the cyclohexanol. Okay, so the cyclohexanol will be having the structure of like this. Okay, ada 6 carbon and hydroxyl group gonna be attached here. But now we're gonna remove the OH and then attach with chlorine so that we can get chlorocyclohexane. So what we're gonna do is that we're gonna do dehydration. Okay, so the process of dehydration means we remove water. So we're going to remove H here and OH here. So that it's going to be HOH, which also refers to H2O. Okay. So when I remove H and OH here, I will get a cyclohexene. Now I need chlorine, one chlorine atom to be added here. So what I'm going to do is that I can react the alkene here with the HCl so that hydrogen can come up here and chlorine can go here. Okay, and this happen in the inert solvent of AlCl3. Okay, so when I add hydrogen to here and chlorine to here, or vice versa, doesn't matter. If you want to get chlorine here, the hydrogen gonna be here, you will get the product here. Okay, and this is known as chlorocyclohexane. Okay, and for the cycloalkane, we don't usually put number 1 at the middle, one chlorocyclohexane, because we don't usually designate the position for one substituent. Okay. Okay, for tutorial question 9, we have to draw the structural formulae of compound in the following reaction. So for tutorial question A, we have the structure of the alcohol here, and then when reacted with concentrated H2SO4 at high temperature, we will produce a major and minor product. So you know that this reactant here will allow the removal of water, which is H2O. So this is a dehydration process. Okay, remove water. So what we can do first is we can remove OH here, and then one of the hydrogen here going to be removed. So when OH and H here is removed, you will form a carbon-carbon double bond in the middle. Okay, so what you're going to have is C double bond C, CH3, CH3, and then you will also have CH3 and CH3 here. Okay, and as what you can see here, this is going to be the major product because this carbon here is attached with 2 methyl group, and then this carbon here going to be attached with 2 methyl group. So total we have 4 methyl group. So this is going to be the structure of A. Okay. Alright, so you can show it nicely here where this is the structure of A. Okay, and for B, we can have another possibility, kebarangkalian yang lain. Okay, so tidak semestinya you take the hydrogen here. You can, for example, OH is you need to take out. You can also take the hydrogen from this carbon, the neighboring carbon. For example, if I were to expand this structure, I will have H, H, and H here, right? So I can remove this H and OH here so that I can form a double bond here. Okay, so if I were to do that, I will get my minor product, which is CH, for example, CH here, and then I'll get CH3 and another carbon chain here. So as what you look into here, this carbon will have 1 and two alkyl group. But this one for carbon, it only attach with hydrogen and hydrogen. So in this case, it only have two substituted alkene. Compared to here, it has four. Okay, so the structure B here gonna be the minor product. Alright. Now for question B, when an alkene is reacted with HBr, the HBr gonna be attaching into the system here. So from a carbon-carbon double bond, what really happened here is that a carbon-carbon single bond gonna be produced. Okay, okay. So in by right, hydrogen would need to be attached with a carbon that has hydrogen. So according to the Markov-Nikov rule, hydrogen need to be placed to the carbon which has more hydrogen. So this is the place that the hydrogen should take. However, with the presence of peroxide, it gonna follow an anti-Markov-Nikov. Okay, so anti-Markov-Nikov means the H gonna be added at the least substituted position. So the carbon bond, the double bond here gonna be a single bond where the hydrogen gonna be attached here and Br gonna be attached here. Okay, and this follow the anti-Markov-Nikov rule. Okay, so you can draw the structure again, and hydrogen gonna be attached at here, and the Br gonna be attached at here, and the hydrogen here is being hidden. Okay, you can draw it out or you can hide it. Okay, so that's for tutorial question 9. For tutorial question 10, we have to complete the reaction scheme. So we have a cyclopentene here and then attaching with two methyl group. So now when it is reacted with acidified water, what they're going to do is that it's going to add the hydrogen and also OH group into the system. Okay, so what we're going to get at the end is that the hydrogen will be added to the more substituted or the carbon which has more hydrogen. Okay, so this carbon here will only have CH3 and carbon chain here, but this carbon will have one hydrogen. So according to the Markov-Nikov rule, hydrogen need to be inserted with the area to the carbon which has more hydrogen bond. So hydrogen gonna be attached here. So C gonna have hydrogen and hydrogen here. Meanwhile, for the OH group, gonna be attached at this position. Okay, so OH gonna be attached here, and as the result, the carbon-carbon double bond will be converted to a carbon-carbon single bond. So this is the addition reaction. Okay, so that's for part A. Now we're going to look into reaction scheme B. Okay, so for reaction scheme B, we have a carbon-carbon double bond as shown here, and now we're going to add bromine and also water. So for this case, the bromine gonna be attaching to this side, which has more hydrogen, and the H2O, which is the OH, gonna be attached at the less to the carbon with less hydrogen. Okay, so this carbon here has no hydrogen, so OH gonna be attaching here. So what we're gonna get is this structure here. Okay, now we move on into reaction scheme C. Okay, for reaction scheme C, now we have the oxidation of KMnO4 using KMnO4 using an acidified medium at high temperature. So when it is oxidized using KMnO4, the double bond here gonna be broken down, and then they're gonna produce a straight chain alkene because it's from cyclic. When it is oxidized, it's gonna form a a straight chain alkene. So what we're going to do is that we label the compound, which is the carbon, which is carbon number 1 here, carbon number 2, carbon number 3, carbon number 4, and carbon number 5. Okay. So for carbon number 1, what they're going to do is they're going to produce a ketone. Okay, and ketone here, because the C here attached with carbon with a alkyl group, and the C here going to be attached with alkyl group, and then the carbon carbon double bond here going to be changed with oxygen. So number 1 going to produce a ketone, and number 5 here, one of them is attached with carbon, and the other hidden bond here is hydrogen. So here going to be producing a carboxylic acid. Okay, so you have to look back in your note if you find this confusing. So now we're gonna draw the structure once again. 1, 2, 3, 4, 5. So what you can do is that you can start with 1. Okay, so if I were to draw the structure, I'm gonna make this bond here number 1 first, which is the carbon number 1 here, and this carbon number 2, number 3, number 4, and number 5. As mentioned, number 1 here will have the attachment with CH3. So attachment with CH3, and then the number 1 here gonna produce a ketone. So C, double bond O, C and C. So these are the functional group of ketone. And number 2 will have hydrogen and hydrogen, which is CH2. Number 3 gonna have hydrogen and hydrogen, which is here. Number 4 gonna have hydrogen and the methyl group of CH3, hydrogen and methyl group of CH3, and number 5 here gonna produce a carboxylic acid, C double bond O, OH. So this is the correct representation. So I will usually use a skeleton structure first, and if you want to use a condensed structure, you can also write it this way. Okay. Now let us look into for reaction scheme D. Okay, so for reaction scheme D, we have KMnO4 at basic condition at cold temperature. So what going to happen here is that a diol going to be formed. So diol means that OH 2 hydroxyl group going to be attached here, and another one OH going to be attached here. So 2 OH group going to be inserted, and the carbon-carbon double bond going to diminish. So what we're going to have is this kind of structure. And now for E, it is a hydrohalogenation process. So for the hydrohalogenation process, it basically remove one hydrogen and one halogen, for example, Cl. Okay, and in order to produce the product here, our reactant need to have one halogen and one hydrogen. So when hydrogen and chlorine is being removed, a carbon-carbon double bond can be formed here. Okay, and at the same time, we can swap the position. Cl gonna be here and hydrogen gonna be there. Okay, so if we remove hydrogen and chlorine by the reaction of KOH and ethanol, we know that we can produce a carbon-carbon double bond. Okay, as shown in the product here. So this is going to be your reactant. Okay. Okay, now for part F, which is kind of easy one. So this is a catalytic hydrogenation. So hydrogen gas going to be inserted here. So at first they have hydrogen, but now you're adding more hydrogen on this side and more hydrogen going to add on this side. And as the result, the carbon-carbon double bond will diminish. So you will get a cycloalkene here. So hydrogen going to add here and hydrogen going to add here. Okay, so now let us look into G. So for G, it is a dehydration process. So you know that in order to produce this product, your reactant need to have OH group and hydrogen here to be removed. So you can say that OH, you know that H is usually is here originally, and you can add OH here and hydrogen here. Okay, or you can change the side. OH gonna be here or hydrogen gonna be here, so that when you remove H and OH, a carbon-carbon double bond gonna be produced. Okay. Okay. Now, if you were to read it back, let's say OH we put here and H is here, we can say that when it undergo dehydration, OH going to be removed and H going to be removed, and a carbon-carbon double bond can be formed as shown here. Same goes to this situation, OH removed and hydrogen is removed, so a carbon-carbon double bond can be formed here. Alright, now for reaction scheme H, now we have to add HBr into the carbon-carbon double bond, but now with the presence of the peroxide here. So the peroxide here means that it will follow an anti-Markov-Nikov. Okay, so anti-Markov-Nikov states that the hydrogen need to be attached at the least with, the hydrogen need to be attached with the carbon with less number of hydrogen. So in this carbon, there has no hydrogen. So hydrogen gonna be attached here and the bromine gonna be attached here. Okay, so with the addition of hydrogen and Br to the system, the carbon-carbon double bond gonna diminish. So what you're gonna get is this kind of structure. Alright, so that's all for question number 10.
For tutorial question 11, compound A C3 has 7 Br, which is an haloalkene, does not react with the cold dilute potassium permanganate solution. So when it does not react with the cold dilute potassium permanganate solution, it basically means it does not have a carbon-carbon double bond. So you know that it is an haloalkene. So upon treatment with the potassium hydroxide in ethanol, okay, potassium hydroxide in ethanol, A gives only product B, which is C3H6. So you know that when the formula gives you a C3H6, it is have a general formula of CnH2n, where you know that it is an alkene. Okay, so let us put the information here. First, we have A, which is C3H7Br, and then when upon treatment with the potassium hydroxide in ethanol, it basically that it undergoes dehydrohalogenation, where dehydrohalogenation means that it removes hydrogen and it removes halogen. Okay, so halogen in this case is bromine atom. So when undergoes dehydrohalogenation by KOH and ethanol, what we're going to get is structure B, which has a formula of C3H6. Okay, so unlike A, B here will decolorizes potassium permanganate solution. So this saturation test here, unsaturation test here shows that B is an alkene. Okay, and ozonolysis of B will give C, which has a formula of, okay, so this is the ozonolysis condition, which is ozone with zinc and water at acidic condition, and then B will produce product C, which is C2H4O, and D, which is CH2O. Okay, now we're going to suggest the structural formula of A, B, C, and D respectively, and we have to write the equation for all the reaction involved. Okay, so these are the equation or the idea that we need to make, and now we're going to do the structural formula of A. So you know that A will have 3 carbon, so you can draw from starting from here, 1, 2, and 3. Okay, so the bromine here you can select to be at carbon at the end at either number 3 or either number 1, or you can do it at number 2 here. It doesn't matter. Okay, so let's say I put the Br at number 1 here, and then when it undergoes the hydrohalogenation, what I'm going to do is that I'm going to remove hydrogen and I'm going to remove my Br here. So when this one is being removed, a carbon-carbon double bond will be formed. Okay, so I will get my carbon-carbon double bond to be here. At the same time, if you want to do your Br to be on this side, you will still get the same product, because when Br is removed and hydrogen is removed, the carbon-carbon double bond gonna be produced as well, and this gonna give the same product. Okay, so this gonna be your structure B. Okay, and this gonna be my structure A. Either one of those. So both are still correct. Now, when B undergo ozonolysis, it will produce C and D. Okay, so for B, when it undergoes ozonolysis, you can see that this one will end with C, and then here we're gonna have a carbon also here. So what they're gonna have here is we're gonna produce aldehyde, and CCH3 here will be maintained, and here basically will have a hidden hydrogen. So what I'm gonna get here is CH3 and hydrogen, which is come from this side, and then the double bond that has been ozonalized will have a carbon-carbon double bond here, a carbon double bond with oxygen here. Meanwhile, on this side, you have carbon, and then you have hidden hydrogen, and also a hidden hydrogen here. Okay, so the carbon-carbon double bond that being ozonalized will form a methanol, which is C with hydrogen and C with hydrogen, and you will have a carbon-carbon double bond, a carbon double bond with oxygen. Okay, so this gonna produce compound C, which has a formula of C2H4O, and then for compound D, it will produce a methanol, which is a formula of CH2O. Okay, so if we were to draw it nicely, we will get our A, where you can also do it in terms of the expanded structure. And when you remove Br and remove one of the hydrogen in either side, you will get an alkene. For example, I remove one of the hydrogen here. Okay, let's see if I expand H, H and H. H will be removed, Br going to be removed, and double bond going to be formed here. Okay, when it is ozonalized, I will get this side C, H, C, CH3, and then I will get a double bond oxygen. So this side going to produce this compound here. Meanwhile, CH2 will get a double bond here and going to produce CH double bond here, which is the methanol. Okay, so that's for tutorial question 11. Now for tutorial question 12, we have to propose a chemical test to differentiate between a butane and a butene. So butane is an alkene and butene is an alkene. So we have to state the observation and write the reaction equation involved in the reaction. So you can use either Bayes test or the bromine test. So let's say if I'm using a Bayes test, what I'm going to do is I'm going to write the structure of butane. So butane here will have 4 carbon. So 1, 2, 3, and 4. So it states here butane. So you know that it's going to be 1 butane. Okay. So you can also draw that in terms of the condensed structure. And for the Bayes test, you're going to treat it with a cold KMnO4 in as in a basic condition at cold temperature. So usually OH gonna be placed up here and the cold condition gonna be placed down here. Okay, so upon the treatment with OH, KMnO4 and at basic condition and cold situation, what we're gonna get is a diol. So OH gonna be attached here and OH gonna be attached here, and the carbon-carbon double bond gonna be diminished. So what really happened here is that OH going to be attached here and OH going to be attached here as shown in here. At the same time, the manganese of MnO2 going to be precipitated down, and this give a brown color precipitate. Okay, so for the observation, we can say that the purple color of potassium permanganate solution was decolorized because initially the color here gonna be purple, but upon reaction with alkene, the purple color will diminish and will be decolorized, and the purple will turn into colorless. At the same time, what we can see in the reaction is that the brown color precipitate, which is the mandakan, will be formed. And this refers to the manganese dioxide here. Okay. Meanwhile, for an alkane, which is butane here, upon reacted with the cold potassium permanganate at basic condition, there will be no observable changes. So what we can say about the observation here is that the purple color of potassium permanganate solution remains unchanged. Okay, and this is how we can differentiate between an alkene with an alkane. So an alkene will decolorizes the purple color of potassium permanganate solution, and at the same time will allow the formation of manganese dioxide, which is a brown precipitate. Okay, so I think that's all for this video. See you again some other time. Bye.